Okay, so we can get started with the final talk of the session and of the workshop. So this talk will be by Alexandr Garbali, and he's going to talk about symmetric functions and quantum toroidal GL1.
Thank you, Michael. And thanks to all organizers for their effort. I guess I can also thank them on behalf of all participants. It was probably not an easy task to manage this workshop, considering different time zones, and also for some organizers to stay awake for many hours at night. Okay, so let me start. I will talk about symmetric functions and quantum toroidal GL1. So this is a part of a bigger project, and inside this project there is a project which computes the R-matrix that defines an integrable model. So at different stages, well, actually, I mean, throughout this project, I worked with Jan de Geer and also with Andrei Neguts, and I will present some updated material on the computation of this R-matrix. So this is all about symmetric functions and Macdonald theory. So I will start with that. I will recap some basics of the Macdonald theory. And I want to switch to the Heisenberg formulation, which is equivalent to the symmetric functions formulation. So I'm going to use Heisenberg operators, and using these Heisenberg operators, I will build Macdonald operators. And the main point of this first part is to write down operators that are diagonal on the Macdonald functions, and their eigenvalues are written using certain specializations of variables. So we'll have several Macdonald operators labeled by a symmetric function, and their eigenvalues will also depend on the same symmetric function. Then I will switch to the quantum group, quantum toroidal GL1. I will quickly go through the definitions, and I will explain its important automorphism, which is very helpful when we look at representations. In particular, well, I will only focus on the Fock representation. And in this Fock representation, this automorphism that I will talk about plays an important role. And this automorphism can be described by this picture. It basically rotates the generators. It switches the basic generators of the algebra. Then I will explain the integrable model, which is obtained on this Fock representation. And this integral model is described by, is given by the R-matrix. So the R-matrix here is not a simple object. Its complexity is similar to the complexity of Macdonald polynomials themselves. And the computation of this R-matrix can be phrased in different ways. For example, it can be phrased as an eigenvalue problem of a coproduct of a certain operator, E0 of the algebra. And then I will go on and explain a formula that comes out from a work of Andrei Neguts. This is an integral formula for a part of the R-matrix. And finally, I will evaluate the R-matrix and explain how to compute the weights of the R-matrix. And this picture shows what sort of vertex model you should expect in this case. And in this vertex model, we have the vector space. The vectors of the vector space are labeled by partitions. And this vertex, in this vertex, we have two partitions which propagate through the vertex, and the number of boxes is conserved. So we have two partitions, they break down boxes, and then they form new partitions. So this would be a matrix element in this R matrix. So let me start with the symmetric functions. So the basic symmetric functions, as usual, are the power sum symmetric functions. We just take sum of all arguments. And we can, we take products of those simple power sum symmetric functions, and this gives a power sum symmetric function labeled by partition lambda. And these power sum symmetric functions, they can be used to build a vector space. And they can be used as a basis in the vector space of symmetric functions. Another important symmetric function is monomial symmetric function, which is given by this, taking all the arguments raising to the power of the partition index and then permuting all variables. So either of these two symmetric functions can be used as basis elements. So let's choose power sum symmetric functions. And using these basis elements, we can define a scalar product, the Macdonald scalar product, and it's written here explicitly. So here we see two parameters, Q and T, and these are Macdonald parameters Q and T that appear in Macdonald theory. So in this talk, I will use these two parameters, Q and T, consistently. Even when I switch to the quantum toroidal GL1, I will also use the same parameters. And this choice is consistent given that I will focus on a particular representation, quantum toroidal GL1. So the monomial symmetric functions, they're useful when we define the Macdonald symmetric functions. So the Macdonald symmetric functions expand in this monomial symmetric function in a triangular way. So there is upper triangular matrix with the coefficients, diagonal coefficients equal to 1, and then we can expand these Macdonald functions in this way. So this is a basis in which Macdonald functions are. This is a triangular basis. So this is one property of Macdonald functions, and then the other property is that it has to be orthogonal with respect to itself. If we keep in mind the scalar product that I talked about earlier. And we can build the dual Macdonald functions by multiplying the Macdonald function with the combinatorial factor. And this combinatorial factor is written over here explicitly. It's some product over boxes in a Young diagram of the partition lambda. So these are some basics. And I want to emphasize that there is of course, a transition between the basis of Macdonald functions and the power sum functions. And I denote the transition coefficients by G. These coefficients will appear several times in this talk. So this is all explained in Macdonald book and its standard material, but I would like to have a slightly different point of view on the same picture from using the Heisenberg algebra. So the Heisenberg algebra is generated by two sets of operators, AR and A minus R with positive index. And these operators AR are called annihilation operators, and these are called creation operators. And this algebra is defined by the commutation relation written over here. And from this relation, it's obvious that the positive modes, the operators with positive index, commute with each other, and the operators with the negative index also commute with each other. So that allows us to build products of positive modes and also of negative modes in a similar way as we took products of power sum symmetric functions. And this defines two parts, two operators labeled by partitions mu. Now the Fock space. The Fock space is defined by the vacuum vector here, and the dual Fock space is defined by the dual vacuum vector. These two vectors have the following properties. The vacuum vector has to be annihilated by the positive modes, and the negative modes, they're used to create new vectors, which are denoted like this. For the dual space, we have, it's the reverse. The negative modes annihilate the vacuum vector, and the positive modes create vectors, create dual vectors. And we can put this vector and covector together to form a scalar product. And using these formulas here and the commutation relations over here, we can calculate the scalar product. And that scalar product comes out as this quantity over here, which precisely coincides with the Macdonald scalar product. And that allows us to conclude that there is an isomorphism between power sum symmetric functions, the vectors labeled by the power sum symmetric functions, and this Fock space vectors built with Heisenberg algebra. And same goes for the dual vectors. So now I recall the coefficients, transition coefficients between Macdonald functions and the power sum functions. And I create an analog, a Heisenberg analog of the Macdonald functions by just taking the sum. So I don't distinguish between this vector and the vector of Macdonald function, and also I don't distinguish between this and power sum due to the isomorphism. So I would like to use this picture, the Heisenberg picture, in order to discuss Macdonald operators. And in the Heisenberg's picture, I will be able to discuss several Macdonald operators on the same footing. And in order to do that, I need to introduce vertex operators. So there are two basic vertex operators, which are built in a special way. We take exponentials of sums of all negative modes with some prefactor, and exponential of sum of all positive modes with the specially chosen prefactor. And then we take another operator, which is similar to the first one, up to some coefficients over here. But the structure is very similar. So this choice is made in such a way that the commutators of two such operators satisfy special relations, and same for these ones. In particular, we can calculate normal ordering of these operators. So what does it mean? Normal ordering, denoted by these dots, means that we want to have expressions in which annihilation operators are put on the right side and creation operators are put on the left side. So this expression means that, so we switch the order of these operators, and then we can remove the dots. So if you take a product of two such operators, you will see that you will have an alternating product of negative modes, positive modes, negative modes, positive modes. And you want to commute the two exponentials of positive and negative modes together. And that commutation comes at the cost of a rational function written over here explicitly. So we can normal order this product at the cost of this rational function, and the result will be given, I mean, the leftover will have ordered product of operators. And same goes for the dual operators psi, except that the rational function is the same as before, but with the arguments switched. You can also view this as inverting Q and T, which is an important remark. So now, for example, if we take products of many such operators eta and we normal order them, then the outcome will have to have positive modes on the right and negative modes on the left. So I wrote it here. We'll take a product of these operators, and we have positive modes on the right and negative modes on the left. And when we collect all these different zi's together, we get the power sum function here. And on this side, we get power sum with negative inverse of inverse arguments. So now I'm going to use these operators to build Macdonald operators, which comes next. So I want to do this uniformly for several Macdonald operators, and this by they all have the same form basically. You have a contour integral over n variables, and you take normally ordered product of this vertex operator that I introduced before, and then sum, and you integrate this with some rational functions. And different operators will correspond to different choices of these rational functions. And then there are dual operators in which we take, instead of etas, we take zetas, vertex operators. So then we have three kinds of operators, E, G, and F, and in which we integrate these etas with this rational function. Then we integrate, so which has a t over here, and then for G, we can integrate it with the different rational function which has Q inverse, and F has a combination of these two, but not quite. So the denominators are the same, but one of the numerators is shifted. So so we have these operators, and we can build dual operators by choosing size. And this is very similar, but you can notice here that we have the inverses of T's and Q's in all expressions. And here I included some prefactors which are important, but they're technical parts. So now I would like to take generating functions of these operators. So I would like to sum each of these operators over n with some generating parameter. So I'm considering this kind of summation. And these operators, they turn out to be diagonal on Macdonald functions in the Heisenberg basis. So we apply these generators on Macdonald functions, and we get back Macdonald vectors. So here are three expressions which are written in a slightly unusual way. I'm using, so this is a power sum, and epsilon lambda is the specialization of the arguments. So I'm taking each argument xi and I replace it with q to the lambda I to the minus I. This is a specialization that appears also in Macdonald book. And I'm doing it everywhere here, and that allows me to view all these operators in similar, on the same footing. So the only thing that changes is this factor, the exponential. So here it's quite simple, and then it's like a platistic substitution or a gauge you can perform on the power sums. You can actually calculate this sum, and you will get just a product of the x's evaluated. And from this expression, you can actually see that this E corresponds to the usual Macdonald operator E from the Macdonald book. This maybe is a little calculation, but if you take E1, you will see that it's just the first term in this generating series will correspond to the first Macdonald operator. So this is some uniform way of writing several operators together. And at this stage, I should give some references. So this integral expression for the e's is due to Shiraishi. This G is due to Feigin and company. And this F, I don't know who to attribute this, but I guess I need to say Andrei Negus. And Andrei has a paper on operators and symmetric functions where he gives many more operators in this same language. Okay, so in the following, I will use only the F and F bar. So this is just for demonstration, the E's and G's, because they are known in the literature. But what is relevant for the model and the quantum toroidal is this F. And its eigenvalues over here. So now I can switch to the quantum toroidal. So I need to start with definitions. The algebra is generated by 4 currents, 2 central elements, and 2 degree operators. These currents are a convenient way of writing together different generators of the algebra. So we can expand these currents in their modes. And these are the generators. And the currents psi plus, psi minus, they're given by exponential generating functions. And here you can notice that I'm using some parameters T and Q, and these are the same T and Q that appeared before. This is slight abuse of notation, but this choice is consistent in the view of the representation that I'm gonna take later. I'm not gonna give the relations of this algebra. I just wanna point out that they are, I'm gonna show one relation, which is over here. This is a commutation relation between 2 E currents, and commuting this to 2 currents comes at the cost of this rational function. And the other commutation relations between E and psi, or F and psi, they're of a similar spirit. It's just that the commutator of E and F involves the 2 psi's over here. That's slightly different. So
can I ask, yep, why is it called GL1 instead of GL2? It looks like SL2 because you have EF and H. Is there a reason it's called GL1 instead?
Yes, there is, and it has to do with the deformation of. So there is a nice explanation where you start with the algebra, this Weyl pair X and Z, and which commute like this, something like this, and then you take powers of X and Z, and so you take generators, you call them EIJ, and then you look at the commutation relations of this. So this reminds, this is more like GL1 because or should I say GL infinity?
Yeah, I think I see. Already that's helpful. Thank you.
But there is, I can come back to this at some other point. There is a nice explanation by Fagin, Jimbo, and others how you deform GL1 starting from this picture, and you get 2 parameters Q and T, but I forget how it goes precisely. Yeah.
Great, thank you.
So even though we have so many generators in this algebra, we can actually generate all of them using commutation relations and this small set of operators. And there is an important feature of this algebra, which is a group of automorphisms, and this is due to Mickey. And there is a particular automorphism, which is most important for us. It exchanges, it basically permutes this set. So we take E0 to H-1, H-1 to F0, F0 to H1, and H1 to E0. and that leaves the commutation relations intact, so they still hold. This is a quite non-trivial automorphism and quite useful. So we can use this automorphism to define another set of generators. So the basic set of generators was given by these operators plus the central elements and degree operators. And by using this automorphism, by applying this automorphism, the inverse of it, to each of these generators, we define a new set of generators, which have this perpendicular subscript. And this picture is quite interesting because now we have two, if we look at the commutation relations of this algebra, we will see two Heisenberg subalgebras here, agent. So I have not shown you these commutation relations. They are part of the definition of the algebra. So now I'm showing them. So we have two Heisenberg subalgebras. And in one of them, we have the central element C in the numerator, and in the other one, it's C perpendicular. So now I would like to focus on the Fokker representation. And in this representation, I'm taking C to be equal to 1 and C perpendicular to be equal to the square root of ratio of Q and T. So when we do that, we immediately notice that this Heisenberg algebra becomes commutative. And this Heisenberg algebra remains non-trivial. And in fact, it can be mapped to the Heisenberg algebra that I was discussing earlier in relation to Macdonald functions. So there is an isomorphism between this and the one introduced earlier, which is isomorphic to the power sums. And it's just, we need to include some prefactors in order to satisfy this commutation relation. So now we can build a vector space based on these Heisenberg elements, and we can consider the action of both sets of operators, these operators and this set of operators. So I will describe this next. So this is due to Fagin, Cymbaluk, and also many other authors who worked on the same problem, but in different language. So the Fokker representation is the highest weight representation, which is characterized in a usual way. We have we start with the vacuum vector, which is annihilated by the F currents. This is a typical situation in highest weight representation of quantum affine Lie algebras. And then the Cartan currents, they act diagonally, and we get this so-called true-infiltrational function, which is used to label representations, the highest weight representations. And the explicit formulas for the action of the operators of the quantum toroidal are written over here. So the normal, not the perpendicular operators, they act as follows. So we have vectors labeled by partitions, and the operators E will add a box in all possible locations. So A lambda is a set of addable boxes to lambda, and we will have some coefficients over here which are factorized. I'm not writing them explicitly because it's a bit of a large formula, but these coefficients are factorized, and if you're familiar with Pierre formula for Macdonald polynomials, you will find that these coefficients are the same in this particular case. And the F's, they act by removing a box from the partition lambda in all possible locations. So R lambda is a set of boxes which are removable from the partition lambda. And again, we have some nice factorized expression, matrix element here. And finally, the Heisenberg operators which commute with each other, they act diagonally on this basis, and the action is given by the same specialization of the power sums as I mentioned earlier. So this specialization takes x is xi to q lambda I to the minus I. And from this description, we can conclude that these vectors here can be identified with Macdonald symmetric functions. And now I can switch to the, so this action is called vertical action in the literature. And there is also horizontal action, which is the action of the operators with this perpendicular superscript. And this action I write using the generating series. And it can be, it's done with the help of those vertex operators that I introduced earlier. So these E-currents, their commutators are, is possible to realize using this xi currents that I introduced earlier. The vertex operators, the exponentials of Heisenberg modes, positive modes, and then negative modes as well. And the F currents, they are realized using this eta Heisenberg operators that I introduced earlier. So now we already see the connection with the Macdonald theory through this vertex operators and Heisenberg algebras. So now this the quantum toroidal algebra is a Greenfield quantum double. So it has an R-matrix, and we're interested in this in the R-matrix in the Fock representation that I just discussed. So the R-matrix depends on the choice of the coproduct, and the choice that we make is in terms of the perpendicular operators, because in this language the Heisenberg elements remain non-trivial. So the R-matrix can be computed using the relation with the coproduct. It has to commute, well, or not quite commute. Delta prime over here is the coproduct where we exchange the two tensor factors. And we get this equation which defines, it's linear equation for the R-matrix, and it defines, basically allows to calculate the R-matrix. It's of course a very difficult calculation if you try to do it, because we have Macdonald operators everywhere. And, so this is the task, to solve this equation and calculate, understand what is this object, what is this R-matrix. And after this, we can evaluate this R-matrix, and the most interesting evaluation is in the basis of Heisenberg in the Fock space. And this evaluation gives the matrix elements that are defined over here. And these matrix elements satisfy the Young-Baxter equation. And that gives the model.
So, sorry, I'm confused, Sasha, about
Yes.
one. How does the R-matrix get a spectral parameter from just this definition?
Good point. So this definition is already in the Fock representation. So the spectral parameter appears. I didn't say that here, but this is directly in the Fock representation. In the Fock representation, we get the spectral parameter in the usual way how we get it in the quantum affine algebra. There is an orthomorphism that allows you to introduce the spectral parameter. So it appears over here, and
Great, thank you. I missed it there. Great, thank you.
yeah, I should have emphasized. It's an important point. So this representation it's labeled by this complex number U, which appears in this way. Yes, thank you. So we get the spectral parameter, and which plays an important role in the Young-Baxter equation. Now, how do we solve this equation? And then so I'm going to discuss this now on some general grounds. The Greenfield quantum double construction and Greenfield pairing for this algebra, we conclude that the R-matrix has to be composed of three parts. There is the degree operator, which is simple, and then there is also a simple exponential factor, with the Heisenberg elements. And what remains is an object that depends on the spectral parameter. So this is the most interesting part. And this object is expanded can be expanded in the Heisenberg operators. This is a general expression that R prime of U can satisfy. So we're looking for the R matrix in this form. And also from the quantum double construction and the degree and the arguments of the action of degree operators, we conclude that there is a conservation property here, which says that if we add this partition alpha and gamma, it has to be, the total number of boxes has to be the same as in the partition beta and gamma and delta. So the total number of boxes here and here should be the same. This is the main conservation law that we have. So now we're trying to solve the coproduct equation. This equation for all elements of the algebra G in the Fock representation. And when we try to choose the Heisenberg elements, these elements, and commute the R prime full R matrix with them, we will conclude almost immediately that we should have actually this form. So R prime expands not in the full set in this large tensor product, but only in two operators, which are written as in terms of the original operators like this. This follows from simple coproduct relation, and it reduces the number of coefficients that we need to compute. So now, instead of having coefficients with labeled by 4 partitions, we only need to compute coefficients labeled by 2 partitions, and this relation holds. So now we can fix normalization so that the two empty labels for two empty labels, these coefficients are equal to 1, and we need to calculate this coefficients R. So this problem can be phrased in terms of the so-called twisted coproduct, but it's not twisted in the sense of Greenfield twist. It's a twist. It's a partial twist by an orthomorphism. So we can take the orthomorphism that I defined earlier and square it. So it simply exchanges the E's and F's together and the psi's and psi plus and psi minus. And if we apply this operator to the coproduct of this current, then we get an operator that will have an interesting action on the vector that I built in this way. So I take the unknown coefficients that I want to compute, and I put them together with 2 vectors, tensor product of 2 vectors. And then there is a theorem in our paper with Jan that says that that this vector R has to be an eigenvector of this twisted coproduct operator. And this equation allows to calculate the coefficients R recursively. And it's explained in our paper. And in fact, we can generalize this problem. This is a side remark. We can ask for all eigenvectors of this operator. And this is also an interesting problem. It reminds us of a problem that was considered by Shiraishi and collaborators, where they try to diagonalize the coproduct of E0. And by this problem, they define so-called generalized Macdonald functions. So in our case, we twist this coproduct and define a new operator. This problem is similar to the problem that they considered. But this is a side remark. So now let me give you another point of view, which is due to Andrei Negud's. So Andrei is using. Yeah.
Just before you go on, so this delta, is it delta sub k? So I missed what.
Sorry, this is U. This is the spectral parameter U because we are assuming a Fock representation. Yeah. So this is in Fock.
Thank you. Sorry.
Representation. So there is an alternative presentation of the algebra, which is called elliptic hole, and it's very interesting and elegant. And this representation, is useful because it has a nice the Fock representation for this elliptic hole can be formulated using shuffle algebra, which is done in several works of Andrei Negud's. And using this language of shuffle algebras, Andrei calculates integral formulas, and he's able to come up with an integral formula for these coefficients R, alpha, beta when they're expanded in the spectral parameter. So for each coefficient of the expansion, it comes up with an integral formula, and we can use this in our language. We can use this result, and this leads to the following proposition. So we have this factor R prime of U that we would like to compute, and after using this, we can write it as a series in the spectral parameter with the coefficients R and prime. And these coefficients are given by the following integral over here. So here you can see this is a rational function that showed up before when I talked about the Macdonald operators, the F operators. Then we recognize vertex operator psi and the vertex operators eta. So if you remember, which is probably very hard, the formulas for the operators F, then if I cover this part, if I remove this part, this will be precisely the operator F bar n. And if I cover this part, this will precisely be the operator Fn, which both act diagonally on Macdonald functions. So from that we have this proposition. If we sandwich this R prime, so we sum over n for all n here, then we sandwich with the first tensor component with the vacuum vector. This vacuum vector, it removes all these operators because they are normally ordered. And then we're left precisely with this product here. And this is the Macdonald operator F. On the other hand, if we sandwich the second tensor component with the vacuum vector, then we will remove this part and we will be left with Macdonald operator Fn. So then taking the sum is easy, and it gives the two Macdonald operators F and F bar. And based on this, we can relate the expansion coefficients of these two operators in the power sums with the expansion coefficients of the full R prime. But I would like to maybe stop here for emphasizing the connection between this R matrix and Macdonald operators. So this was the motivation of the title, I guess, that there is a nice connection between the R matrix and Macdonald operators. So now I can expand these operators in the Macdonald basis, and then further expand this Macdonald basis in the Heisenberg basis. And that gives me a way of calculating explicitly matrix elements of R. So I need to recall the transition coefficients, Macdonald 2 power sums. And then I'm going to introduce modified coefficients, G, which just have some extra gauge factors, and G bar. They have also other gauge factors, and the B coefficient from the Macdonald theory. And then this expansion that I mentioned earlier, so this F, if we normalize it properly, then we will find that it expands diagonally in Macdonald basis, and this will be the eigenvalues which are computed from those exponentials that I mentioned earlier. So this gives this has this nice U dependence, and it has some poles. And so using this expansion, we can calculate explicitly the matrix elements. Which are written here in this proposition. So we have some factor, common factor, and then we have a summation over two partitions alpha and lambda. We have two Macdonald coefficients, transition coefficients of Macdonald functions, and then we have the functional dependence on U, which shows what are the poles of the R matrix. And then there is also a connection coefficient written in terms of binomial coefficients. So this is not the most, the simplest R matrix you've probably seen in during this conference. But you've seen probably many R matrices and L matrices which are used for calculation of Macdonald polynomials and other symmetric functions. But here, we're using Macdonald functions to calculate R matrices. So this is a kind of reverse problem. But this formula is somewhat minimal that you can achieve by trying to calculate the matrix elements R. And the complexity of this formula is the same as the complexity of calculating Macdonald functions, the power sum basis. So I used the indices here, nu H, nu V for horizontal and vertical, the same for the mu's. And the picture here, the graphical picture corresponds to this. For example, if you look carefully at this picture, you can see that if you take this to be empty and this to be empty, then everything will collapse and you will only have one Macdonald coefficient, and the same goes for the two other coefficients. You will see only one Macdonald coefficient, and of course the dependence on the spectral parameter. So I can now show an example, some simplest cases for those partitions. So when they're all empty, then we get the initial condition that we started with. But when they're more interesting, for example, these two are empty and the other correspond to a single box, then we calculate explicitly. So these G's can be computed, and then we get only two terms in this expansion. And in this way, we can calculate many matrix elements. For example, the first 6 elements, they are shown over here. So we have a 1, then we have some simple factors. And then for the 6th one, we have this expression, which has 1 plus t, and then this factorized part. So in this in this form, it was convenient for me to replace q with the t times another parameter q tilde squared. It's just for convenience. But if you remember the 6 vertex R matrix, then you will immediately see it over here. And this will be the 6 vertex R matrix with the deformation parameter q tilde, which is equal to q over t. So it's going to be the R-matrix of this quantum affine algebra. So unlike the cases of which were discussed by Michael, when you work out symmetric functions using ut to the 1/2, actually there is 1/2 over here, or uq to the 1/2. This is a bit different. It has uq over t to the 1/2. And this is the final thing that I wanted to mention. And I guess this is the end of my talk. Thank you.
Okay, thanks, Sasha.